Welcome to the second lecture of this week, and in this week we will be talking about the most important topic of this week, or the important cuts. So this is going to be our key concepts, okay, and we will try to deliver that key concepts to you in a minute. Okay, so let's recall some of the basic definition that we had. Okay, so definition is delta R, remember, is a set of edges with exactly one endpoint in R, and a set of edges is a minimal xy cut if there is no xy path in G minus S and no proper subset of breaks every xy path. And we also saw that every minimal xy cut S can be expressed as set of edges leaving a set of vertices R, okay, with is equal to delta R for some x subset of R, and R intersection Y is empty. So for example, look at these four edges, they are like delta. Now what is an important cut? So this is our basic and most important definition, as it is like the idea is that, look, I'm going to call a cut important if number of edges which are emanating out is as much as my current cut, but I am further from myself. I contain more vertices than R itself. So, and a minimal xy cut, okay. So let's just add where are we? Okay. So what is an important cut? Is basically, imagine that I'm going to tell you that, look, here is my x and here is my y and this is my r. Okay. So what is my what do I want from this? I said, look, okay, or rather let's say R is not important. What is the meaning of R is not an important cut? This is the way we will use. It means I'm going to tell you, oh, if R is not an important cut, then I can find another set. What can I find? Another set R prime. And what is the property of R prime? First of all, R prime is delta of R prime is less than equal to delta of R. So the number of edges which are leaving R prime is at most as much as R had, but more importantly, secondly, R prime intersection Y is fine. So basically R prime is also an XY cut, or rather let's say R prime is also an XY cut, but more importantly R is a proper subset of R prime. So I have been able to achieve the following, that R prime is proper subset. R prime contains R completely properly, and the number of edges that you need to disconnect X from Y via R prime is at most as much you needed to disconnect X, Y by deleting edges which were adjacent to R. That's all. Okay, so this is what. So, or in the other words, what is an important cut? A minimal XY cut delta R is important if there is no XY cut with the following property. You cannot give me another, like, if there is no XY cut delta R prime with the property that R is a proper subset and delta R prime is less than equal to delta R. For example, look at this. Look at these four edges. Okay, look at these four edges. Now, can you contain? So you have to ask, is R an important cup? Well, look at this. Can I add this? If I add, is delta R an important cut? You have to ask this question, right? It may not be an important cut, because if I take this guy, look at this cut, what is the property? Number of edges are 3, and this, if I'm going to call it R prime, contains R properly. Okay. Now you can ask yourself, okay, so firstly, can we check if a cut is important? We will see how to test whether a cut is important or not in polynomial time. But for now, let's just try to understand the concept of important cut. So what is an important cut? A cut is important if I cannot find another cut with the property that the number of edges or the cut size is at most the current cut size and it properly contains R. So for example, this R is not an important cut because this R is not an important cut because I can find an R prime with a property that R is a proper subset of R prime and delta R prime is actually strictly less than delta R because delta R had 4 edges, this has 3 edges. Okay. Okay. Now, so for example, this, if you take this R prime, I gave you another example, but look at this R prime. I could have taken even a bigger R prime, right? Now, what is the property? Look, definitely R prime contains R as this. It had 1, 2, 3, 4 edges. It also has 1, 2, 3, 4 edges going out. So this is also important. But, right? And I told you another one. So there are several reasons why. But what about this? Okay. Now let's ask ourselves. So definitely this particular R was not an important cut because we could find an R prime with at most 4 edges and properly containing R. And remember, always disjoint from Y, which I am not taking. But what about this R? Now there are 3 edges. Now notice, if you add to R this vertices, then that's not good for you because then you will contain 4 edges. Okay. So you like, you take this, you will still get 4 edges. I mean, you take anything, you will still get 4 edges. But here we only had 3 edges. So and for R to be not an important cut, we have to produce an R prime with at most 3 edges emanating out of it. But in R, if you add any subset of these vertices, you will get at least 4 edges leaving, which implies that this R is an important cut. Okay. So, yeah. Okay. Now let's ask ourselves, how will we check whether R is an important cut or not? Okay. That's very easy, how to check an cut is important or not. Okay. So how will we check an cut is important? We'll say, okay, fine. I'm going to call a cut. So suppose R comma Y. Okay. So now look at, just compute R comma Y. Okay. R comma Y, I'm going to call, compute a cut R comma Y, cut between R and Y. Okay. A min cut. A min cut in R comma Y. What can happen? Either, so if I compute a min cut, then I will get some another R prime containing R and Y outside. And it's a min cut. So notice, I check its value. If this value, whatever this, if the delta R prime is less than equal to delta R, okay, and R prime and R is a proper subset of R prime, then what we know? Then we know that there exists such an object. So for example, so this is all that we need to do. But you may ask, well, what about that if delta R is equal to actually, so look at this delta R prime. Suppose delta R prime is equal to delta R, then what he could have written? you could have returned. So let's ask. Okay, so let's just do slightly simply. Okay, so you are given an R and XY cut. Okay, and what I need to do, if R is an important cut, right? R is an important cut. Okay. So what I'm going to do is the following. Okay, I'm going to call what I'm going to call. I want to find RY cut, right? So X I replace by the. I want to find a cut between R and Y. Okay, and I'm going to find a min cut. Okay, a min cut. Okay. So if the min cut is, so suppose I return some R prime. What could happen here? Notice, if delta R prime is strictly less than delta R, then clearly R prime also properly contains R and you are done. Okay. But what could happen is that delta R prime is actually equal to delta R, and in this case you might just return R prime equal to R. You could just return R prime equal to R. Okay. Okay. So but that doesn't mean that R is an important cut. R is an important cut. This doesn't mean that R is an important cut, because for R to be an important cut, we have to say does not exist R prime such that R is a proper subset of R prime and delta R prime is at most delta R. So we know that we cannot have at most strictly, because it's going to be equal. So now what will we do? Okay, you say fine, compute R max for R comma Y cut, right? So what is the property? It is, so you know that the min cut between R and Y is same as the number of edges living. Now you want to contain a furthest cut, a cut which is furthest from this. So R max for RI cut of size delta R. If R max is also equal to R, then you know that R is an important cut. Else not, right? So given an R comma Y, I can check whether it's an important cut or not by computing RY min cut. If its size is strictly less than the delta R, then you already know that it is not an important cut. But suppose this is equal, then you compute, so you know that delta R is a min cut between R and Y. Now you computed R max with respect to this delta R, right, of size delta R, and if that, you know that's unique and you can find that in polynomial type, we have seen. If that is also equal to R, then only you know that R is an important cut, else we know that R is not an important cut. So this is how we can check whether a given cut is an important cut or not, by just computing a couple of min cut algorithms, running couple of min cut algorithms. And let's see how many number of important cuts can be there. Number of important cuts can be exponentially large. Okay. Okay. So suppose we have, this is basically the whole graph. So this graph has X, there are k by 2 vertices, and there is another k by 2 vertices, and there are some middle vertices with path. Now what do you know? Your min cut, or rather, and you are looking for a important XY cuts of size at most k. What is an important XY cuts of size at most k? An important XY cuts of size at most k, I am going to tell you that, okay, you decide which vertex of this k by 2 of this path is going to be part of this, and which vertex from middle vertices. For example, if I pick this, and pick this vertices. Okay. Now, what is the cut size? Because look, it's a k by 2 vertices. The number of edges which are adjacent will always be less than k. Say some k prime. Now, this is an important cut. Because why it is an important cut? Because to be not an important cut, if this is one word, you cannot take the vertex of y, because you have to be a disjoint from y. So then what does it mean? It means that you can only pick for the vertices that you have picked from x in your. So look at an important cut, which consists of this. I'm going to call this an important cut. Why? Because look, the moment you pick anything from here, the cut size will increase by +1, right? Any moment you pick anything else, cut size will increase. So just by numeric value, it will not happen. So how many such this thing? It is, so number of important cuts of size at most k is upper bounded, like is possibly you choose a subset from x and then the corresponding. So it's, since the size of x is k by 2, the number of important cuts is at least 2, like 2 power k by 2, right? Because you just pick a subset of size this, and then, so basically R consists of, let's call it either a subset of x and say y, and secondly a subset of x, say y, and neighborhood of x. So the moment you pick, so suppose this is my y, right? So, and what else do you have to pick? R, neighborhood of x minus y, which is this vertices. That's it, right? That's it. So how many such objects are there? Number of such R is upper bounded by 2 to the power k by 2, because the moment you guess a subset of x, everything gets determined. So the number of important cuts in a graph can be exponentially large as a function of k. Okay, but what we are going to prove, that there are at most 4 to the power k important xy cuts of size at most k, and that is our important theorem. That the number of, so here's a lower bound, but what we are going to show, the number of important cuts, xy cuts of size at most k is upper bounded by 4 to the power k. And towards that, we are going to give you an algorithm. Okay, it's a branching algorithm with a very beautiful measure. Okay, so let's see that branching algorithm. So we are going to show that there are 4 to the power k important xy cuts of size at most k. Notice, let lambda be the minimum xy cut size and let delta R max be the unique important cut of size lambda, such that R max is maximal. You know that there is a one R max which is maximal and it's unique. Okay, so we are going to show that if you are looking for, so here it is, my x and y, and this is my R max. We are first going to show that R max is a subset of R for every important cut delta R. Every important cut delta R, R max is a part of this. So that will be our starting point. So let's first show this property. Again, we are going to use sum modularity. Okay. So what are we going to apply sum modularity? Okay. So here is your R max, and here is your R, and here is your x, here is your y. Okay. So we are going to apply sum modularity on R max and R. So by sum modularity of R, delta R max plus delta R is delta R max intersection R plus delta R max union R. But what is a delta R max? It is a min cut. This is R max, is this. So this is min cut. So this is exactly equal to lambda. And what is a delta R max intersection R? This is also a cut between x and y. So its value is also going to be greater than equal to lambda. Okay. It's at least greater than equal to lambda. It could be even further, but it is definitely greater than lambda. So what will you get then? So then delta R max union R is delta R max minus delta this. So this is upper bounded by delta R. Okay. So if R, so what we know that the R max union R, look at this. It is at most delta R. So if R is not R max union R, then delta R is not an important cut, right? Why? Because what are we able to show? Look, so we are able to show to you that look, number of edges which are going here is at most delta R, right? Is at most delta R. Then look at R max union R. R is definitely contained inside this, right? So if R is a properly contained inside R max union R, then that's a contradiction to the fact that then that is a contradiction to the fact that R is a important cut, because its value is less than equal to delta R, right? And it contains properly. So, but that is not happening. Okay. So what is the meaning of that? Okay. Thus, the important xy and R max y cuts are the same, and hence we can assume that x equal to R max. Okay. So what are we able to show? So what did we get a contradiction to? We wanted to show that R max is a contained inside R. Okay. So if R max is not contained inside R, it means there is some vertex here, which will imply that R is a proper subset of R max union R. And if R is a proper subset of R max union R, then that will imply that R is not an important cut. So by contradiction, what we know that R max is properly contained inside R for every R. Okay. So what we know about this? Thus we know that the important XY cuts, right? Important XY cuts and R max Y cuts are the same, right? So whether you are talking about important cut from X to Y, or you are talking about important cut from R max and Y, they are same, because R max is part of every important cut. And that is why we will assume that X is equal to R max. Okay. So we assume that X is nothing but equal to R max, because our first lemma has shown that this is exactly, because lemma has shown that R is like R max is contained inside every, so you are not going to lose out any cut. Okay. So now our search tree algorithm for enumerating all this. So you look at this X and look at this Y. You pick up an arbitrary edge UV leaving X equal to R max. So what is the property? Either this is part of an important cut, or it is not a part of an important cut. Okay. So if it is not a part of an important cut, then what can you say? Okay. So first, imagine that UV is part of an important cut. If UV is a part of an important cut, then S minus UV we will show is an important XY cut. But what is its size? Now its size is K minus 1 in G minus UV. So what is my algorithm will do? It will say, okay, fine. Let's enumerate all important cut of size K minus 1 in graph G minus UV and add UV to each of these cut. That will consist of all important cuts that contains UV. Okay. Fine. Or we know that UV is not part of S. Then what I know, then S is an important X union V, Y cut of size at most K. Then I know that, okay, fine, UV is not in S. If UV is not in S, in the important cut, then you're trying to get a cut of, put a V inside X union V, and you are only talking about cuts of X union V and Y, because any cut that you're talking, important and non-important, is also have to contain both X union V. So, but it's cut in size at mod K, right? So, we have been able to branch into stages. What? Either this edge is part of my important cut, or it is not part of my important cut. If it is not a part of my important, if it is a part of my important cut, I delete and I look for a cut of size K minus 1, find them all, add UV to each of this. In the second branch, where I'm looking for an important cut that doesn't contain UV, then I know that I'm looking for an important cut of size X union V, comma, Y. Now our question is two questions. Why this branching is correct? It's exhaustive, that is fine, because the correctness, because why it is exhaustive? Because look at important XY cuts. Either it contains UV, then you are counting them in branch 1. It is not contains UV, then you are counting them or putting them together in branch 2. So this is exhaustive. This is absolutely correct. Why the branching steps are small, why these things are correct, we'll see in a minute. Okay, we'll see in a minute. Okay. So what happens in the first case? Look at definitely K decreases by 1. But it could happen that the min cut size also, the min cut between X and Y also decreases at most by 1, right? It's possible because like it can only decrease by 1. You cannot have min cut size suddenly because becoming lambda minus 2 because you have just deleted 1 edge. This is not possible. Then because then you take this lambda minus 2 edges, add that edge, and that's an XY cut of size at most lambda minus 1. That is not happening. So it is possible that lambda can decrease, min cut between X and Y could decrease by 1. But what happens in the second? K definitely remains the same. But what is the property of R max? The property of R max is that if I add any other vertex to this, the min cut between X and Y must increase, right? It must increase at least by 1. Because if it would have remained the same, then R max is not the unique cut. You could have put the V, and that would have been an XY cut of size at most lambda. So even though K remains the same, lambda, the min cut value increases by 1 between X and Y. So there is something changing. Now see what happens. So if I use the following measure, 2K minus lambda, okay, then what happens? Okay, so look at this, okay, so it is 2K minus lambda to start with, and the change in measure is 2 times K minus 1, and look, lambda decreases by at most. So if it is just lambda, then you check 2K minus lambda minus 2K, that will get cancelled, and this is minus lambda plus lambda, that will get cancelled, and you will get minus 2 plus 2. So in this case, there's a drop of 2. But what could happen, that lambda could also decrease by 1, and in this case drop is at most by 1. Okay, but look at this case. This is like 2K minus lambda minus 2K minus lambda plus 1, and if you do this, this is going to come to 1. Okay, so but what is the total value of 2K minus lambda? 2K minus lambda is at most 2K. So height of the search tree is at most 2K, and each branch search tree drops by at least 1. So the total number of important cuts of size at most K is upper bounded by 2 to the power 2 power K, which is 4 to the power K. So that there are 4 to the power K important cuts of size at most K. Okay. So what are we using? So now just try to get some feeling of the correctness. Okay. So we are going to show to you that if UV is in S, then S is an important XY cut in G, implies S minus UV is an important XY cut in G minus UV. Okay. It's not true. So let's see why this is true. So look at it. S is an important. Okay, we'll see. Okay. What happens? So suppose this is an important XY cut. Then I want to show that is an important XY cut in G minus UV. So suppose this is an important. This is R. Okay. And this is an UV, and this is an important cut. Okay. Now imagine that S minus V is not an important cut in this. It means what? I can find another R prime, okay, which contains R properly and has at most K minus 1 edges going out. Now look back this R prime. then this graph and this graph only differs by at most 1. So maybe there's one more edge going out from R prime. That's all that can happen. But then what does that imply? Then that implies that R itself was not an important XY cut in G, right? Because I could have taken R prime as because R prime would dominate R. R prime is a better cut than R, right? So this is what it implies, that if you give me an important XY cut, it definitely remains an important XY cut in G minus UB. So if you are able to upper bound the number of important cuts in G minus UB, that will indeed provide an upper bound on number of important cuts in G that contains UB. Okay, but there's another interesting thing. Converse is not true, and an important cut in S minus UB may not be an important cut in original graph. Meaning, so if you give me an important cut in G, it is definitely an important cut in G minus UB, but an important cut in G minus UB may not be an important cut in G. So basically, number of important cuts in G minus UB could be potentially much larger than important cuts in G itself. Okay, but that's not a problem because we are only trying to get an upper bound number. Okay. Okay. So for example, Y, look at this set. AB and AY is an important cut in G minus XB, right? If you delete G minus XB, then this and this is an important XY cut. But if you go back to the original graph, okay, to the original graph, right? XB, AB and AY is not an important XY cut in G. They are not an important XY cut in G, right? So a cut which is important here may not be an important there. But what about the second case? S is an important XY cut in G if and only if F is an important X union B Y cut in G. This is easy to show. Let's try to show formally. Okay. So suppose S is an important XY cut in G. Okay. And we are in the premise that S is an XYB cut. Okay. We are only talking about those kind of cuts. So, okay. And so this is basically continuing to XYB and Y outside. This is an R. And it is an important XY cut. Why is this not an important XY cut in G? I mean, what does it mean that it is not an important XY cut in G? Well, you will say, okay, fine, I will go take more R prime, number of edges is at most K, blah, 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 and say. But then, I mean, then that contradicts the fact that R is an XUV union Y XY cut. Okay. And similarly, if S is an important XYB cut in G, then you can show that S is an important XY cut in G. So this is if and only if. So in this case, you don't lose anything. I mean, you don't gain anything, let's say. And here, you might gain many more things. Okay. So what happens is that at the end, you might get lots of cuts. You know that the number of cuts generated by this is 4 to the power K. But you have to filter out important cuts because you know that you would have also got some cuts because of the branch 1 and they were just important cuts in G. You made them a potential cut in G minus a potential cut of G by adding UB to it. Not all this may be important cut. So you check which one of these are important cuts. Okay, check which one of these are important cuts and only enumerate these. Right. So you collect a family of sides, say 4 to the power K, that contains all important cuts, and then you clean this up and only enumerate important cuts. Okay. So here is our algorithm. Handle trivial cases. You find R max. Choose an edge UV of delta R max. You recursion G minus UB, R max Y K minus 1, recursion R max union V, Y comma K, and it check if the return cuts are important and throw away those that are not. As I told you that some of the cuts that you could get may not be an important cuts, right? So you have to test them, check them, and throw them out. Okay, so the last thing of this lecture that I would like to tell you, that there are just now, sir, there are at most 4 to the power important XY cuts of size at most K. We also saw a lower bound of 2 power, we also saw a lower bound of 2 to the power K by 2. But in fact, we can actually get an essentially tight bound of 4 to the power K. How do you get this is again a very similar to the example we had. You consist of binary tree, okay, such that number of leaves, say Y, is greater than K. That's it. First time you get this is all that you have. And you just add a pendant, call it X, and every leaf is your Y. Okay. So here, okay. Now look at a subtree here with at most K leaves. Okay. So this is bind. Any subtree with K leaves will give you an important XY cut of size at most K. Why? Suppose look at this. Okay. How do you get? Look at the leaf and delete these edges. Okay. That your cut edges. Delete these edges. Right? So how many edges you have? At most K edges. Okay. But notice that for a set that contains this, the moment you pick any other vertex, number of edges that is adjacent will increase by at least 1. Okay. So the moment you go beyond this set to slightly larger set, the cardinality, the number of edges will strictly increase it, and hence they cannot be important cut. So any subtree with K leaves gives an important XY cut of size K. How? Again, let me repeat again. You look at the leaves and the edges which are adjacent to these leaves, that will be exactly as many as leaves. So they are bounded by the number of leaves, hence their number of at most K. And for any other important cut must contain this set, no? So the moment you pick any other vertex containing this, the number of leaves, number of edges going across will increase by whatever it was. And hence they cannot be an important cuts. And hence they cannot be dominating this. So every subtree with K leaves gives an important XY cuts of size at most K. And it is well known fact, I will not going to show this to you, that the number of subtree with K leaves is a Catalan number, and it is given by 1 choose K, 2K minus 2K minus 1, which is roughly at least 4 to the power K poly K. So this also tells us that the number of important cuts in a graph is upper bounded by 4 power K, and roughly that's a bound is tight because there are a family of graphs and examples where you do have at least roughly 4 to the power K poly K divided by poly K number of important cuts. I think that is a good place to stop, and in the third lecture we will see the first application of important cuts in a problem called multi-way cut. So we will talk about multi-way cut in the third lecture. Thank you for now.